Thank you for having us here today. My name is Matthew Flaming. I anchor the site engineering and data services teams at New Relic.
I'm Nic Benders. I'm the chief architect.
And we're here today, indeed, to talk about how we've scaled the New Relic platform. And this is really a problem that every successful software engineering organization faces at some point. How to evolve systems under load to meet growing demand, changing requirements, all of that without dropping customer data or causing a service interruption. This is something we've had a lot of practice with, and we're hoping to share some of the lessons that we've learned specifically scaling the part of the New Relic platform called our data tier. So these are the systems that accept data from our customers sent via the New Relic agents, ingest that data, process it, store it, and make it available for querying.
But there's something even better, which is our safe harbor slide. So we want to talk about this just for a minute. This document and the information herein, including any information that may be incorporated by reference, is provided for.
Okay, let's talk about the New Relic Cloud.
Oh.
So, as you heard Lou talk about earlier today, this is really a pretty amazing piece of technology. We've developed a supercluster that is always on, multi-tenant, massively scaled, massively performant. It's a pretty unique system. So when we talk about scale at New Relic, there are really two key points to make. The first aspect of scale at New Relic is what we think about more traditionally. It's the number of requests we handle, the amount of data we process. And these are what I think we technically call pretty big numbers. This is what the New Relic platform is doing every minute of every hour of every day, 365 days a year.
And you already heard a few of these numbers from Lou earlier in the keynote today. There's something I want to call out about these that I'm not going to debase myself like Matthew and use a qualitative word in front of unique, but we're going to say that this accepting over 16 million requests, this is a huge amount of data coming into our system, but at the same time, our customers don't just want us to collect the data, they want to take that data and make it immediately available for them to query. And so the biggest number on this slide is actually how many data points we're querying. So the data has to come into us continuously, has to be processed, persisted, and made immediately available. In order to do this, we have a system that's scaled in another dimension. We talk about scale also in terms of complexity. We have the software analytics cloud is really over 200 different services that make up just the production environment. In order to make that data queryable quickly and efficiently, we've written it to solid state disk. We have a giant quantity of solid state disk. And all of this is done by 25 engineering teams who are all in that system every week, building new systems, deploying, maintaining, troubleshooting. And so this is complexity in the organization, complexity in terms of just scale of data that's already there, and complexity in terms of all of the different systems that have to work together.
So over the next 20 minutes or so, we'd like to really go through some of the lessons that we've learned in the process of scaling this system and tell the story of how we have specifically scaled one aspect of it. And our goal is for you to be able to take some of these nuggets home, talk about them with your teams, and hopefully learn some of this in a way other than we did, which is the hard way in a lot of cases. But to begin this story, I think we need to first back up a little bit to 2011.
So in 2011, our system was a lot simpler. This is what our data pipeline looked like. So we had our agents, which ran on our customers' application servers, and they would send data back to us once a minute and into our data collector. It was a nice new system we had just built out in Java, much more performant than the old Ruby-based one. And we wrote it out to the databases, and it was all pretty happy. And this is the world that we lived in 2011. This is blue tier at the bottom, is that same data pipeline. But then we introduced something new, and we made our lives harder. This red tier is our first browser product. So for those of you who've been New Relic customers for a while, this was the Real User Monitoring, or RUM, product. And it really changed the equation for us, because it meant that instead of just taking in data once a minute from each of our customers' application servers, we were taking in data once per page load from each of our customers' browsers.
Right, so we launched this new product, and it took off. In fact, it really, really took off, to the extent that before too long, this new category of traffic actually had outgrown our first APM offering. So in order to handle this load, well, what did we do? We did what I think most development organizations would do, which is leverage the infrastructure that we already had there. We already had our data collection system in place. It was working pretty well. So what we did is we built a new system to the side of it called the beacon, which would accept this new category of traffic and forward it on to the data collector. Pretty soon, we rolled out another product offering, mobile monitoring. And to support mobile monitoring, well, we did the same thing all over again.
But this type of organic growth was not without drawbacks. So whereas previously we had a system that was well understood, it served a single purpose. The application agents, which could buffer data locally, would report data to the collector. The collector would write that data to the database. If there was a performance hiccup, the collector couldn't write its data this minute to the database. It would ask the agents to hold the data, send it again the next minute. So then once we introduced these new systems attaching onto the side, then that same type of small performance problem in the database became a big problem for us throughout the system, where a performance issue in one database in a collector could cause problems in these multiple products.
So the other thing to keep in mind is, of course, while we were wrestling with these problems, we weren't doing so in a vacuum. Our traffic kept growing, and in fact, we were very aware that the traffic growth we had seen so far was actually just the prelude to even more traffic growth in the future. And this really brings us to, I think, the first lesson that we want to share today, which is that nothing lasts forever. When we build a piece of software, it's very natural to get attached to it, to think, OK, we've created this beautiful architecture, and we can keep extending it and modifying it to meet changing needs. But the reality is that sort of attachment gets in the way of critical thinking quite often. And the reality is, sooner or later, a piece of software is going to outgrow its founding assumptions, and incremental isn't going to cut it anymore. And instead of just tweaking what's there, it's going to be necessary to take a big step forward.
So like a lot of our lessons today, this one is cultural as well as technological. The issue wasn't just that the software that you built couldn't handle the load or the complexity of today's system. It's that the decisions that we made back in 2011, 2010 were good decisions, and they were the right decisions. They don't become wrong decisions when the complexity of the system grows. What you have to do is you have to be able to identify this, go back and cut a point and say, you know what, we need to look in a new direction. So at New Relic, when we look in new directions, we think about experiments. We pride ourselves on having a culture of experimentation, both in terms of things like management process, just how we structure our engineering organizations, and also how the technology itself works. So the experiment we devised here, we said, you know what, we've been dealing with this hard sharded model for the last several years, and we're just not able to get enough throughput into the database. So let's introduce an intermediate proxy tier that allows us to spread that load instead of going to a single database into many, many more databases as we grow. And so you see here this orange line, which is that proxy tier, as we began to roll it out into more and more of our customers.
Great. So unfortunately, what we found is as we had added more collector instances, more databases, we had also horizontally scaled our single points of failure. So the same sorts of propagation issues that we were seeing before, where a slowdown in one place would impact multiple systems, well, we were now just seeing that on a larger scale. And we realized that, OK, this is probably not the direction that's going to work for us. So we adjusted the experiment. And our next iteration of the experiment was actually going even more all in on the proxy tier and saying, you know what, we're going to try funneling all of our traffic through this, not just some of it. Maybe that'll create more equilibrium in the system. We had a few reasons for thinking so. Turned out we were wrong. We went into that experiment, and as you can see, pretty quickly we pulled back out of it. There was one little piece we kept, which was a proxy for our mobile product. You can see that in the dark blue stripe up there. But on the whole, really wasn't a success.
So this is a really important corollary to that lesson about running experiments, which is that experiments don't always work. This is why we call them experiments. And we didn't do a great job handling this the first time. That initial rollout, which was not successful, went on for longer than it needed to for us to learn that that wasn't the right direction. We did better with that second part of the experiment where we tried another approach. In a very short period of time, we were able to say, you know what, this approach isn't working at all for us. But even still, we did learn a number of things while running these experiments. So I think having the opportunity to do it again, we want to focus on that iteration speed and move through those experiments more quickly and be sure we have hard exit criteria, but it wasn't a total loss. The most important thing that we learned during this is that synchronous calls are going to be a problem. The root of our issue wasn't that we didn't have enough databases. We could add more and more and more databases. The problem was that a slowdown in a single database would propagate upwards through the system and cause problems not just for the component it was attached to, but also to the upstream components around it. So by this point, we realized that what we needed was to change the system in a way that would absorb those shocks.
So for our next experiment, we really took a step back and thought, OK, what would this pipeline look like if we took out the synchronous pieces? And what we ended up with was an architecture that was asynchronous, message-driven, and looked essentially like this. So at the top, we have a set of browser data routers. And the job of the data routers is to just slurp incoming bytes off the network and forward them onto a set of Kafka queues. So Kafka is a log appender reimagined as a distributed message queue. And it's a technology we chose because it's what's called a very low back pressure system. That means the behavior of systems that are reading data out of Kafka, consumers, has very little impact on the behavior of systems that are pushing data into Kafka, producers. So you have a good decoupling between those systems. On the other side of our Kafka topics, we have data consumers that are pulling those messages off of these message queues, doing browser-specific processing, storing some of that information off to the side, and then forwarding that data to our legacy collector via another set of Kafka topics.
And so I want to underscore something that Matthew just said there, is that this collector architecture over here on the side, this is really still that same legacy component. Because there's a lot of business value in the software that we had already written. Now, it wasn't performing perfectly for us. There are things we wanted to change, but it also maintained a lot of complexity inside it, had a lot of our business rules built into it. So instead of replacing it outright, what we did is we developed a new pipeline that would still talk to that same system while eliminating the most common failure mode for us. So now, when we look at that same scenario again, what we see is the same database slowdown. It has that same reaction to the collector. The app agents already know how to deal with this. The collector now is pulling off of Kafka more slowly. This is where that low back pressure aspect of Kafka became really critical to our business, is that when we stopped taking information off of Kafka as quickly, instead of having its queues start to grow and the system become harder to work with, it has a fixed performance in any situation around that. So all of the upstream components continue to work fine. Once the performance blip had moved on, we were able to process the backlog and start going. So in reality, this is what the rollout looked like for us. Again, in red, that's our browser traffic. As Matthew said, we had just eliminated our proxy component for the most part. So we introduced up there at the top in that yellow tier is the new experimental browser traffic for our browser beta. And that's another thing that we learned, is that instead of going straight for an existing data stream, we first tried this out with a new data stream that we thought would be a good model, but also a challenging problem that needed solving. And we were able to work with that for a number of months, get all of our tooling and our practices down right, and we'll talk about those more in just a minute. And then after that, proceed with a more wide-scale rollout.
So by this point, we were pretty convinced that we'd actually found a good answer for our problems. This experiment was a success, is what we wanted to do. So what was the next step? Well, the next step for us was to then say, all right, let's turn this into a generalizable pattern, because we'd like to have more or less the same pattern throughout our data tier so that it's very easy to reason about. And we don't have snowflakes sitting out there. And again, this is what that pattern looks like. Data routers reading bytes off the network, forwarding data to a set of Kafka topics from which the data is read by a set of consumers that do things like aggregation, normalization, enrichment, so on and so forth, and then send that information on to a variety of data stores and databases, including, of course, NRDB, which is a very massive one, but we use also other specialized data stores for different types of information, depending on what the write and read patterns are going to look like. Then on the other side of that, we finally have a set of retrieval services. So the new Relic products that use this data and expose it to customers via API or UI can talk to these systems without knowing too much about the specifics of where things are stored. And this, of course, gives us great flexibility to upgrade and refactor the back end of this data pipeline as necessary without needing to touch all these other components. So having formalized this, we then went ahead and did a rollout across all of our different data streams and products, and ended up with a pretty consistent data tier that is largely what our data platform looks like today.
And this calls out another one of these technical and cultural lessons, which is that you have to master the rollout. In a system where you're trying to make these incremental changes, you're experimenting with things, you're always growing, you're always facing new problems, the most important piece of your technology is, in fact, how technology is delivered. So we needed to really take some time and invest in our ability to bring new features live, to run experiments, and to do all of this without our customers ever seeing an error or noticing that we were changing underneath the entire system they were talking to.
So there were really two core strategies that we used for these rollouts and continue to use today. The first is the incremental rollout. So when we built our new data pipeline, we exposed the same API as our legacy data pipeline. And what that meant is we could use our load balancer cluster, or DNS, to incrementally move traffic over. We would start by moving over 1 or 2 accounts for a couple of hours, make sure it's performing the way we want. If there are issues, roll them back, make changes, rinse and repeat, moving over incrementally more and more traffic for longer and longer periods of time until we got comfortable doing things like, leaving it on overnight, which is actually a big step for us, or leaving it on over the weekend, which is another big step. So this let us do this rollout in a very controlled manner with a safety net there at all times. The other significant approach that we took is what we call the dark deploy, and this is actually something that is made possible by the use of Kafka. So you'll see on this diagram there are 2 browser data consumers. There's, first of all, a consumer that is in the critical pipeline. There's also a V2 consumer with a dotted outline. Now, since multiple consumers can each read the full set of messages out of Kafka without interfering with each other, what that means is we can introduce new versions of the same component, have them actually be working against our production data stream in real-world conditions, and test them out, well, in the scenario they're going to be working in, before we commit to rolling them into our production critical pipeline and making them responsible for data results that customers see.
So here you can also see this dual use in Kafka. We initially went to Kafka because it's got this great low back pressure model. It's a very high throughput component. But it enables us to do things like this because of those aspects, things that we hadn't originally thought of as reasons to make that technology shift. But once we understood the technology, it's giving us a point of leverage to be able to make operational changes like dark deploys, other things that we can do in our architecture now that we couldn't do without it. The load balancer tier is another one of these points of leverage. Even for systems where we're not moving across a dispersed backend, having that point of leverage lets us do things like shifting traffic from one set of endpoints into another set of endpoints, as Matthew said, back and forth, and experiment with those. So it's very important when doing your rollouts to understand what are the capabilities of your environment, where are your points of leverage, and know those tools. We found this also to be true in general, is that whenever you introduce a new technology, you're going to have some new challenges dealing with it, and also new opportunities. So Kafka, for us, was a completely new technology when we started this process. And so along the way, we had to figure out the basics. We found that all of these tooling challenges fall into 3 categories. They're either we need new ways to monitor new technologies, we need the tools to build around it, and we have to operationalize it and figure out what our runbooks are going to be and how to run this safely in production.
So earlier, when we saw the rollout of the browser pipeline, there was a very long period, about 6 months, where we didn't fully commit to this new Kafka-based system. That wasn't because we were having problems with Kafka. In fact, from day one, it worked very well for us. And it wasn't because we were having problems with the other components in the architecture. It's instead because we felt we didn't yet have enough maturity to really operate this thing reliably in production, to know how we are going to scale up and scale down our clusters, to know how we're going to do upgrades, to know what people need to be involved if there is an incident. So investing very heavily in this is what let us feel safe rolling forward just as much as the production testing of the systems themselves.
And then once we had this in hand, the next step for us was, we said previously, to roll forward throughout the rest of our environments. So we see here that the full browser traffic stream has been moved over. As we move from 2014 into 2015, we see that for the first time, that bottom tier, that traditional data pipeline that we talked about at the very beginning, is now being replaced by a new architecture. We also see our analytics events moved into there and our mobile monitoring moved into there. So at this point now, we have all of our data streams are all moving through this new architecture, and it gave us a chance to see how it works in different environments and to find the opportunity to find a few more challenges along the way. One of the most important is that the workload distribution in an asynchronous system is very different from an asynchronous system.
So, in fact, getting the workload distribution right has been one of the more significant things that we've spent time thinking about as we've rolled out these systems. So it turns out that really there are 2 fundamental models for workload distribution in an asynchronous system like this. The first model is active management, and this is the model where you have something like a traffic cop near the top of a pipeline, and that traffic cop is grouping together messages either by category or into approximately equal-sized buckets of work and handing those out to downstream consumers that are going to process the workload. So there are a few great advantages to this sort of approach. As you can see over here, we have things like very good data locality. All of the A's are in one place, all of the D's are in another place. That means that, for example, things like caches can be very, very efficient, since a given cache doesn't necessarily need to know about the whole universe. It also means that doing operations that span multiple messages or groups of messages are much more computationally efficient. So aggregating messages together, you can do all of that in one place.
But it's not all good news. The problem with the active management system is that in order to set your workloads correctly, you have to know what the workload's going to be. So it works great for an environment where you can approximately size ahead of time how much of this goes into this category or how much of this goes into this other category and segment the work in an intelligent manner. If you're dealing with a rapid traffic spike or some other situation where you don't understand the environment or your assumptions are wrong, the active management system is going to cause you a lot of trouble. So a random distribution, on the other hand, it assumes you live in a world where you don't know what you're doing, which is strangely accurate for many of the things that we do. And so the work stream comes in, and we just allocate it as quickly as possible to an available worker. This way, if there's suddenly a huge burst in the number of C-type items that are coming to us, they're just going to be absorbed the same as if they were more B-type items. It doesn't create a system that's unstable for us.
So it's true that you get better work distribution under more circumstances with random partitioning. The problem there is that the efficiency of your caches goes way down, and things like aggregation become much more computationally expensive. So what we ended up doing is actually using both approaches in different points of our pipeline. Near the top of our pipeline, if you recall that diagram up by the data routers, we're using a random distribution approach. At that point in the pipeline, we really aren't doing a lot of heavy lifting around messages. There's very little state that we're retaining, so the random model works very well for us. Farther down in our pipeline, where we are doing more stateful operations, the active management approach ends up being much more efficient.
So the key isn't to use one or the other. The key is to find the spots in your system where the correct distribution can be applied. And like us, perhaps, you'll end up with a hybrid system. Along the way, we also learned about kind of a broader pattern in the software architecture, which is that your technology enables your culture. And we've talked about this as a few of these touch points along the way, that a tool like Kafka isn't just a way to connect components. It also changes the way that your business works. So when we think about Kafka inside of New Relic, we often think of it like the New Relic data bus. This is the place where you can put your data and get everything ready. I'm sorry, I'm laughing at the bus. I cracked myself up. But you put the data onto the bus, get everything ready to go, and other teams can interact with it. And that's what we've seen, is that this is a diagram of the production components that talk to Kafka. The ones that are in green were developed by the data services team who built Kafka for their own purposes. But all those blue components are maintained by other teams. They didn't have a part in the creation of the Kafka tool, but once it's there, they say, oh, this data is interesting to me, I can connect to it, I can interact with it, and this allows our organization to have these stronger boundaries between teams and lets us build software more efficiently, not just run an environment more efficiently.
Taking a step back, another lesson that we've learned from all of this is really about this life cycle of software architecture in general. So seen from about 30,000 feet, this is really the set of steps that software systems go through during their life cycle. We start out with something new, a new paradigm, a new set of assumptions. We build a great system. And over time, that grows organically as we add new functionality, new capabilities. And at a certain point, you reach a breaking point where the system has outgrown its foundational assumptions. Incremental isn't going to cut it. You need to take a big step forward. And at that point, it's back to the new paradigm again.
And we can see this story over the elements that we've illustrated here for the last several years. We started with a new paradigm. Our Java-based collector worked well with the agents, got the data into the disks. We grew it organically to add more and more components, but the combination of complexity and throughput really brought the system to its breaking point. And we said, this isn't going to work for us anymore. It's time for us to go again with a new paradigm. We've introduced the new paradigm, which is our asynchronous system. The asynchronous system has been rolled out to the rest of the world, so we're growing it organically. But we have good confidence that it won't last forever.
So if we look back over the complete story we've told, this is the growth of New Relic. And as you can see, we've evolved the system quite a lot to get to the point where we are today. There have been, you see things coming and going, traffic shifting around between different stripes. But the important thing for us to remember is that the pinnacle we're at today isn't a finish line. In fact, it's just a starting point for tomorrow's growth. So the biggest lesson here for us is don't get cocky. Remember, nothing lasts forever. Remember that you need to make experiments, and some of those experiments aren't going to work out. Remember that there's a life cycle to software systems, that at some point, what you're doing now that makes you feel so confident about your success is actually going to be tomorrow's idea that isn't quite cutting it anymore. And when that happens, of course, you need to be ready to look ahead and get ready for the next new paradigm. Thank you very much.
Thank you, everybody.